This is Chapter 8, Problem 7. And it says, consider a too small space habitat that consists of a rotating cylinder of radius 4 meters. If a man standing inside is 2 meters tall and his feet are at 1 g, what is the g force at the elevation of his head? Do you see why projections call for large habitats? So here we have a centripetal force, which, by the way, is the support force of the side of this rotating space station. What keeps him from falling towards the middle is his own inertia, as he is attached to the floor and rotating. His body wants to go out, and that's what we mistakenly call a centrifugal force, which doesn't exist. But there's actually a centripetal force that, instead of course making him go out here, pushes him towards the middle, and that's the floor. So the floor pushes towards the middle, and then the centripetal force, this is actually on the right hand side of Newton's second law, is written as m times v squared over r. And now they're saying, well, what if we equate that with his normal weight? If he was on the influence of gravity, well, that would be then mg, and the v squared over r is the g, with the mass actually being inconsequential as far as the acceleration is concerned. Okay, now it says at r equals 4 meters, this is the case. But what happens at r equals 2 meters? So half the original radius. Well, at half the original radius, where his head is, of course the r here is 1/2 of the original value, and then his head here, which is half as far out, takes only half the circumference. That means that the tangential speed is also just half. So the tangential speed where his head is 1/2 of the value of his feet on the outside. His feet need to take the long way, and therefore have a larger tangential speed than his head. And of course both are rotating in the same amount of time. Okay, that one needs to be squared. And now when we look at it, we come up with that we have a half squared here and a half here, which means one of them divides out, and we're just left with 1/2. And when we equate that to what we had earlier, that means 1/2 g. So his head experiences 1/2 g, only 4.9 meters per second squared, towards the middle. And so I guess I would make for a little lightheadedness if you experience an appreciably different acceleration due to gravity, so to say, in your head versus your feet. So to avoid that, the space station is made appreciably bigger. Chapter 8, Problem 8. And it says, if the variation in g between one's head and feet is to be less than 1/100th of a g, then compared to one's height, what should be the minimum radius of the space habitat? So again, the equation would be similar as we had before. We would have v squared over r, and at the feet that would be g. But then 2 meters further in, we would have to come up with just 99% of that, because it says 1/100th in a difference. So less than feet is to be, the variation in g is less than 1/100th, which means where the head is, it would be 99/100th of g. And what we saw in the last calculation would mean then that our v and r both would take on 99 100th r, 99 100th v, and we square that, just like it says for centripetal force. And so that's how we come up with 99 over 100 on the right hand side. And now we say, okay, the radius or the head is just 100th further in of this radius. So 99 over 100th r means that we have a variation of 100th of a radius, and that is equivalent to 2 meters, and that means that r equals 2 meters times that 100, which comes out to 200 meters. So at a radius of 200 meters we would feel g, and at a radius of 198 meters where our head would be, we would feel 99% of g, and I guess the difference is small enough that we don't get lightheaded. This is chapter 8, problem 9, and it says, if a trapeze artist rotates 1 second each second while sailing through the air and contracts to reduce the rotational inertia to 1/3 of what it was, how many rotations per second will result? So angular momentum is conserved, and angular momentum can be written as the rotational inertia times omega, which is the rotational speed, and this here would be once per second, which can be written like this. Second to the negative 1 is once per second. Now the rotational inertia is reduced to 1/3 of its original value, but the equal sign has to be valid, so that omega here needs to be 3 times as large, and therefore she will have to rotate 3 times per second.